Welcome to our next slideshow lecture on the forces involved in shaping the surface of the Earth. So today we're going to be talking about some new information. So last week, to review, we were talking about the theory of plate tectonics and evidence that we have that plate tectonics is happening. And so far, all that evidence has been static evidence, meaning like things that we can look at, like maps and layouts and rock formations, locations of fossils, things that aren't currently happening in front of our eyes. So the question then is, what experiments and data can scientists gather of things happening right now to support this theory of plate motion on the surface of the Earth? And this picture should give you a clue about what I'm asking about. So take a minute to think about what you might say if I were actually lecturing. Well, yeah, the biggest dynamic thing, the biggest thing that's changing about the crust of the Earth, or the biggest evidence of change, is earthquakes. So today we're going to be focusing on earthquakes, what they look like, what causes them, and how we measure them, and what information they give us about other aspects of the surface of the Earth. All right, so it's important before we go too much further on that we talk about um, earthquakes in different locations. So today we're going to be focusing on earthquakes that occur at plate boundaries. But I did want you to know that there are other earthquakes. Earthquakes happen for a variety of reasons. So earthquakes are the release of energy in the crust of the earth, and there's a lot of different reasons for energy to build up. So oil drilling and mining are examples of man-made earthquakes where our activity in the crust builds up enough force to make a measurable impact on the seismic activity of the area. So I know that Oklahoma right now is actually dealing with a spat of um, over the last like 5 years or so. They've been measuring a whole bunch of earthquakes that they think are because of fracking in the area. So humans are shoving a whole bunch of water and sand, not just water, liquid and sand, into the earth. That builds up pressure, and that pressure is eventually released through different earthquakes. So oil drilling and mining are examples of man-made earthquakes. There are also earthquakes like the ones along the New Madrid Fault. So the New Madrid Fault is not a fault at a plate boundary. It's in the middle of the United States, where Arkansas, Tennessee all meet, and it travels northward. Um, and it is actually a leftover fault from two supercontinents ago. I forget what the supercontinent was called, but they believe that this old supercontinent tried to break up in different places, and this area of the continent tried to split, but wasn't quite hot enough. So I think if you remember from last week, the convection zones where here we can back up, where heat is coming up from the center of the mantle. So these areas, they create ridges in the crust where the plates start moving away from each other. Now these are formed when you have a new upwell of heat in one area. Well, they think in this particular plate that um, there was an upwell of heat that wasn't quite enough to split this continent in half. It cracked it, it made it weak, and had some upwelling of magma and stuff, with different volcanic rock seeping into that area, but it didn't fully form into a rift and then into an ocean in the middle. It just made a fault, which makes it weak enough that with the stresses of motion of different plates, you get some earthquakes happening there. So the and those there are other examples other than the New Madrid fault of like partial faults um, away from plate boundaries, but that is one example in the United States. And then finally, volcanoes also cause some earthquakes. So these are four examples of earthquakes that don't occur at plate boundaries. But from here on out, we're just going to be talking about earthquakes at plate boundaries. So, why do earthquakes happen? I want you to actually answer this question if you can. Pause the video if you need to. And think about it. Rocks want to stick together. So, why do earthquakes happen? Well, there's friction between rocks. All there's friction between all objects, but you've got interlocking rock formations, rocks that were formed together or next to each other or are just next to each other right now, and the molecules individually, if they're part of an interlacing structure, want to stick together, but also just bodies of rock together. If you put one rock next to another and press them together and then move them next to each other, that's going to cause friction. So friction is a resistive force. A resistive force means as the plates move, the direction of the force is going to be opposite the direction of the, the direction of the friction force is going to be opposite the direction of motion. So it's going to resist whatever motion is happening. So we said plates are moving, so therefore there must be friction. Well, what happens when we drag two objects in opposite directions that have a lot of friction across each other? So think about like if you had a box that was attached to a rubber band. Um, well, the obvious answer is that they'll stick together. But in more detail than that, they're gonna if they continue to move, they will build up potential energy. So imagine you're dragging a box of something across the ground and you're holding on to a rubber band. So you're dragging it using a rubber band to hold on to it. Well, it's going to jerk and slide. Well, as the rubber band gets stretched out enough that the force is enough to counteract friction, then the box will jump. But as it jumps, it releases the tension that's built up in that rubber band. So the force is then not high enough to counteract friction again, and the box will stop. So it'll jerk and slide, jerk and slide, jerk and slide. And that jerk is going to be different depending on the motion in different situations. So it's not always going to jump the same amount. Well, you can think about rocks the same way, except the rubber band is the earth itself. So you're building up tension, you're building up that extension of energy, that elastic potential energy in the rocket itself, and then suddenly jerk, the fault slips, and you release a bunch of energy, but then that energy isn't enough to keep it moving, so it stops again. So it's important to notice that faults are moving all the time, and they don't necessarily release that potential energy all at once. There are examples of what's called creep. So where faults move slowly relative or constantly relative to each other, and you get these cracks in the ground like this. This is an example of what creep looks like, where Earth just slides slowly by each other. Or you can release all of that elastic potential energy all at once. That is what an earthquake is. And different faults and different rocks, different types of rocks, are going to release larger or smaller amounts of energy at once. So if you had a fault that was made entirely out of sand, obviously it's not going to have huge jerks and slides because sand is just going to rub right past each other with not a whole lot of forces. So you have a lot of sandy sediments. You're going to be in like a slip fault. You're more likely to have creep, whereas other types of earthquakes and other types of rocks are going to have, sorry, other types of motion and other types of rocks are going to result in earthquakes. So earthquakes are the violent release of energy, of potential energy. I should write that. Earthquakes are The violent release of plastic energy in rocks. That's your definition for earthquakes. Smaller. You get to see my PowerPoint edits in real time. Congratulations. All right, so that's what we're dealing with. All right, well, when faults crack, I said that the amount of energy is released is different for different types of faults. So let's look at those different faults. So a normal fault occurs at diverging plate boundaries. So remember, diverging plate boundaries are moving away from each other. So let's look at what that looks like. All right, so no more fault as they move away from each other. That is what happens. So we'll look at it again. They move apart. One slips lower relative to the other because they're moving away from each other. Okay, not too bad. Well, at these normal faults, you're only going to have small and infrequent earthquakes because at diverging plate boundaries, you have high rock temperatures. So remember, diverging plate boundaries um, are where new crust is being formed, so that magma is welling up from the surface uh, at the surface and slowly cooling. So that because it's hot, that rock is more plastic and isn't gonna crack and break really easily. It's more moldable. So you have small and infrequent earthquakes at diverging plate boundaries. Well, at converging plate boundaries, the opposite is true. So you've got old, hard, cold crust, and this is what happens in a so these are called thrust faults, where instead of moving away from each other, these are moving away from each other in a normal fault. In a thrust fault, they're crushed together, and one part of rock is thrust upward relative to the other. There are also things called blind thrust faults, where the surface itself just deforms and the crack only happens further down. So I'll show that again. So this part moves up relative to that, but instead of cracking at the surface, it just deforms, which happens more often. So these are called blind thrust faults, but they're both the same category where you have converging plate boundaries. Okay, well, at converging plate boundaries, you're going to have the largest earthquakes ever recorded. So this is the opposite of diverging plate boundaries. Converging plate boundaries are super violently thrust together, and you get magnitude 9 or higher. You can get magnitude 9 or higher earthquakes in these locations. Those are the largest ever recorded. Okay, well then the third option is for the third type of plate boundary. Strike slip faults happen at slip plate boundaries. We also call them transform boundaries, and they look like this. Pretty simple, right? You're moving laterally relative to each other, so you crack and move sideways. That is a slip fault. So those are the three options, and the earthquakes that happen here are large, but not as large as the large converging plate boundaries. Well, we're talking about large and small and medium size earthquakes. So how do scientists measure the magnitude of earthquakes? That's our next question. So scientists measure earthquakes using what's called the Richter scale. The Richter scale is a logarithmic scale that measures the amplitude of the earthquake waves. So, logarithmic means that for each number that you go up, the size of the reaction, so the amplitude of the earthquake wave, goes up by 10 times. So, back here, If I had a magnitude 9 earthquake at a thrust fault, and then I had a slip plate fault earthquake that measured at an 8.0, so which is about the large, that's about the scale of strike slip fault earthquakes. So magnitude 8 earthquake here and a magnitude 9 earthquake here. Well, you just went up one number, but because it's a logarithmic scale, the magnitude 9 earthquake has 10 times larger amplitude of earthquake waves. So the size of the motion going back and forth is 10 times larger a magnitude 9 earthquake than a magnitude 10. So that is a huge difference. That's why magnitude 4.0 earthquakes you can hardly feel, and anything below that you can't feel at all. Whereas magnitude 9 earthquakes literally rip the earth apart, they knock buildings over, they break nuclear power plants like the one in Fukushima, Japan. The magnitude 9.0 earthquakes or higher are catastrophic. So keep that in mind. Also, remember from our waves unit, amplitude and frequency are the things that determine the wave of the amplitude and frequency of a wave are the things that determine the amount of energy in that wave transmitted by that wave. So the Richter scale determines how much energy was released in that violent reaction. So we were talking about the stored up potential energy. The Richter scale is a measurement of how much energy was stored and then released suddenly. All right. Well, I want you to you can do some of your own experiments with two pieces of cardboard, or you can just imagine doing it. If you take two pieces of cardboard and shove them into each other, is it going to take more or less energy than if you take two pieces of cardboard and slide them laterally next to each other? Well, the obvious answer is that pushing them, shoving them into each other is going to take a whole lot more energy to make them move. So that's why the largest thrust fault earthquakes are the largest ever measured was 9.5 in the Andes in Peru, or might not have been Peru, it might have been Chile, but it's in the Andes. Whereas the San Andreas Fault, so the longer your slip fault is, so remember back here, slip faults are the ones moving laterally relative to each other. Well, the longer the fault is, the more energy you can store up. So the San Andreas Fault is the really long slip fault in California. The maximum earthquake size that can come from that fault, according to scientists, is around 8.3. That's what they predict. Well, there's a bunch of faults in California. The one most relevant to us is the Rose Canyon Fault at San Diego. It literally goes through downtown San Diego. I live a couple miles from the fault, but the maximum earthquake that could happen from there is estimated to be around 7.0. So more than 10 times lower than the San Andreas Fault one, which in itself is more than 10 times lower than the largest earthquake ever recorded. So the largest earthquake that could happen in the Rose Canyon Fault is 100 times, more than 100 times, smaller than the largest earthquake that ever happened. There's one other scale that scientists use to measure to describe earthquakes, and that's the Mercalli scale. Sorry, and it's a measurement of how destructive that earthquake is. So just because the amplitude of the wave is really large doesn't mean that it destroys a lot of things. So part of it is the amount of energy built up and released, but also the type of ground that is being shaken. So if you have a 9.5 earthquake that's shaking a bunch of rocks, well, rocks are a more stable footing for buildings than a bunch of sand. So if you have an earthquake traveling through rocks, then you're going to have a lower value on the Mercalli scale than a really large earthquake traveling through sand, which would cause a whole lot more destruction. But the most common number that you see is the the Richter scale, not the Mercalli scale. So we're going to deal primarily with the Richter scale. All right. Well, we're the thing with earthquakes is that different waves are caused by this violent release of energy. So there are two types of waves created in earthquakes. Well, we've already talked about the two major types of waves in our waves unit: longitudinal waves, which, if you remember, are side to side or push-pull waves. These in earthquakes are called P waves. The P stands for primary. We'll talk about why they're primary waves in a minute. But this is an animation that shows what they look like. All right, so primary waves, P waves, are side to side. So if you look at this particle, it moves to the right and then to the left. So primary waves travel through the Earth side to side. And they are longitudinal, like I said, and they also travel faster than S waves. This is because it's easier to transmit energy side to side in materials than to travel it to convert it into potential energy and then release it downward like a transverse wave does. So that speed difference is really important. So pay attention to that. Primary waves, longitudinal waves, travel faster than S waves, transverse waves, and you can remember that by if you remember that sound waves travel faster through liquids than through solids than through liquids than through gas. So the more dense a material is, the faster it travels. Well, primary waves, push-pull waves, are a longitudinal wave just like sound, and they travel through liquids and solids, whereas S waves don't travel through liquids at all. So we'll get to that in a minute. So S waves are secondary waves. They're transverse waves and they travel slower. They're an up and down motion similar to the ocean, and they can't travel through liquid. That's important. S waves, secondary waves, cannot travel through liquid, and we'll show why that's important in a minute. But let's look at a secondary wave. So secondary wave is this up and down motion. So different S primary waves side to side, secondary waves up and down. Okay, place. Well, if we know that primary waves travel faster and secondary waves travel slower, we can do this thing called triangulation. So a detector, if you set it up to that and it knows the speed of two different types of waves, well, you can measure the distance, the difference in time of arrival. So if I'm here in Los Angeles and I get two sets of waves from an earthquake, first I get primary waves, and then a couple seconds later, secondary waves arrive at my station in Los Angeles. Well, I know due to some basic, well, not some math, some algebra. I can use algebra to calculate exactly how far away that earthquake happens. Well, that tells me that that earthquake happened somewhere on this circle. Well, if I radio a buddy up in Portland and I say, hey, I just felt an earthquake. It happened this far away from me. How far away did it happen from you? Well, Portland does the same calculation and he says it happened this far away from each other. Well, that tells me that the earthquake either happened here or here where our two circles meet. Well, if we want to nail down exactly where that earthquake happened, we call up a third buddy in Salt Lake City who does the same calculation, and he says it was the further away of those two objects. So, triangulation, you need three sets of data, and you do some algebra with the different types of waves to calculate the exact distance away that earthquakes happen. So the earthquake detectors that we have laid out throughout the world use this method to determine exactly where a earthquake happens or is centered at. And you can use it in 3 dimensions to actually find how deep the earthquake happened and yeah, you need I think you need a fourth detector three dimensions to use triangulation, but the idea is the same as what GPS uses and all of that. You use the speed of the wave that travels through rock to measure the difference in time of arrival, and that gives us our location. So that's how scientists measure where earthquakes actually happen. All right. Well, it turns out that you can use this information, these different waves and their different speeds, to figure out a whole lot of really cool things. So, scientists use the properties of waves to discover incredible information about the Earth. So, I want you to think back to last week when we were talking about the different layers of the Earth. So, we said we have the crust, the upper mantle, the regular mantle, the outer core, and inner core. And I said these are made of different materials. First of all, I said that the mantle, is liquid, and that's what allows it to circulate this way. Well, I lied. I was wrong. First of all, well, we'll get to that in a minute, but let's look at a diagram. So take a minute to look at this diagram. Pause the video if you need to, and remember that we said P waves, primary waves, and S waves are different types of waves, and they travel through different materials. So I said that primary waves travel through liquids and solids, and S waves travel through only solids, or they can't travel through liquids. So take a minute to look at this diagram and tell me what you can discover about it. Pause the video here. All right, so maybe you made these observations and maybe you didn't. Well, first of all, I noticed that all of these waves trajectories are bending. Why would waves bend? So remember from our waves unit, we said light doesn't bend, it travels in straight lines. Well, that's basically true, but it also bends at the boundary between one material and another. Remember that? That's called refraction. Well, if you have a slow and steady increase in density, you're changing the material that wave is traveling through. As you change density, you're going to change the direction of that wave through refraction. So all of these waves are slowly and steadily refracting as they travel through denser and denser materials. And then that density changes as you go further out, so you bend less and less. So these waves refract as they travel through the mantle. Well, that's one thing we know. So if we're on the surface of the Earth, we use triangulation. We figure out an earthquake happens here, and then I call a detector all the way over here in South America. Hey, here comes an earthquake, and they measure an earthquake that traveled through the center of the Earth, and they got P waves and S waves. Well, that's interesting because S waves, remember, can only travel through solids. So that means that the mantle actually has to be a solid. So let's go back to here. I lied last week. The mantle is not a liquid, it is a mushy solid. It's mushy enough that it does flow, but it's solid enough that it transmits secondary waves. It's actually like in between a solid and a liquid. It flows slowly over time, but it's solid enough to be defined as a solid for the purpose of secondary waves. So that's confusing, I understand, but you can think of the mantle as a moving solid. Well, now let's look here. The S waves reach the outer core and then stop. So this is how we know 100%, we are 100% confident that the outer core is liquid, because out here on the other side of the Earth, we don't get any secondary waves, none at all. So an earthquake happens on the other side of the Earth, no secondary waves are transmitted through to the other side of the Earth. You have to take really detailed measurements to actually get these things, but we have earthquake detectors all over the surface of the Earth. That's the really exciting thing about geology right now is we're living in an information age where we have information about a whole bunch of things that we can use to determine these things. And this is how we are confident about the structure of the Earth. We can't drill through the crust. We can't even get down to the mantle. Yet we are confident that the inner part of the Earth is liquid. Well, finally, the very inner section we say is solid. So remember last week I said the inner core is solid. Well, in part, we think that because of the speed the waves take traveling through. But the other reason we think it's solid is because we know the pressure and temperature that it is at, and we know from mass measurements what material it's made out of. At least we have a strong we have strong evidence about that. So we are confident that the nickel and iron core of the Earth, when it's under enough pressure and temperature, will be a solid, whereas out here in the outer core, that iron and nickel will be liquid. So we use modeling to determine what this is made out of, whereas this is measured using these materials. So this experiment, remember we were talking about, so what evidence and data can scientists take to measure things? Well, we took a whole bunch of data about where earthquakes happen and the speed that those waves travel at, and the location that we measure those waves at around the Earth when they happen to determine the composition of our entire Earth. That is really incredible information that we wouldn't be able to find in other places. But we know this transition from solid mantle that flows to a liquid inner core to a solid core is based on this evidence from earthquakes. All right, that's it for this week. Not too bad of a lecture, but the questions are going to be posted on a separate document. Good luck.